Um, so this is A-level AQA chemistry topic 3, completely patterned. Yeah, we're gonna go through the whole topic here. Also, got the summary questions here, all of that. Yeah, we got the whatever sheets and that as well. Yeah, and any questions here, send it to the email and I'll respond in it. Alright, calm. Let's get to this then. Yeah. So, ionic bonding. Yeah, ionic bonding occurs between a metal and a non-metal. Electrons are transferred from the metal to a non-metal. Yeah, so easy. Yeah, magnesium. Yeah, has two electrons on the outer shell here. In order to have a complete outer shell, it needs to lose these two electrons because deep if that goes, yeah, then this whole outer shell goes and reveals the inner one, and the inner one will be full, yeah? Calm. Now, it's gonna give one, yeah? So oxygen needs two more electrons, yeah, to fill its outer shell. Once it has the outer shell full, yeah, one, two, three, four, five, six, seven, eight, it will have, yeah? So once it has eight electrons, then it's patterned, it's calm, yeah? So this is gonna lose two electrons, yeah? And it's gonna give it to the oxygen. The oxygen is gonna gain two electrons. The oxygen is gonna become two minus, yeah? Whereas the magnesium is gonna become 2 plus because it lost two electrons here. And these are perfect now. 2 minus and 2 plus will attract to each other, so that creates a bond between them. Do you understand? Very easy, yeah? When electrons are transferred here, it creates charged particles called ions here. Oppositely charged ions attract through electrostatic forces here to form a giant ionic lattice here. So obviously because of this, you have like here sodium chloride here, NaCl here. Obviously when you see on the table salt here, NaCl here, you don't just see it as one grain of NaCl in it. You see it as like an actual structure. It's not like a molecule size here. And that's because the NaCls they form this structure here where you got sodium and you got the Cls, the black dots here, and it's surrounded on each side. And as a result, it creates that powerful, huge structure to the point where you can see with your eyes the grain of salt here. Alright, calm. Compound ions here. So you got some compound ions you need to know about. Sulfate is SO42 minus, hydroxide is OH minus, nitrate is NO3 minus, carbonate is CO3 2 minus here, and ammonium is NH4 plus here. Calm. Covalent bonding, yeah? So covalent bonds form between two non-metals here. Electrons are shared between the two outer shells in order to achieve a full outer shell, yeah? Multiple electrons can be shared to produce multiple covalent bonds. So with a covalent bond, yeah, atom A, yeah, needs one more electron to be full, yeah? Atom B needs one more electron to be full. Now, atom A and atom B, instead of one giving to the other, because if atom A gave to atom B, yeah, then that's it, it's finished, it's peak for him, yeah. He lost that electron in it, you know what I'm saying? So yeah, then he would have, you know what I'm saying, only six, yeah. So in order for them to both achieve a full shell, what they do is they combine like this, yeah, and they share the electrons. Now A technically has eight, and B technically has eight, yeah. That's called a covalent bond. This can happen with more than one electron shared, yeah, and that multiple covalent bonds form, yeah. Calm. Now you get something else new in A level, yeah, called coordinate bonding, yeah, or dative bond, yeah. A coordinate or dative bond is a covalent bond that forms when both electrons come from the same atom, yeah. So my man is losing, he's missing two electrons. So what happens here is you see this atom, it has eight already. This atom shares two electrons, so all the electrons that were shared came from the same atom, yeah. Whereas previously one came from A, one came from B. Look at the shared one. One's red, one's blue. Whereas now, yeah, they're both yellow, fam. Do you see that? This is called a coordinate bond, yeah? Calm. Metallic bonding, yeah. Metallic bonding occurs of a consists of a lattice here of positively charged ions surrounded by a sea of delocalized electrons here. This produces a very strong electrostatic force of attraction here between these opposite is places between, yeah, these opposite charged particles, yeah. So basically the a metal, yeah, it doesn't just exist on its own. It's not an atom like size, yeah. When you look at a metal, you see like a brick of iron or whatever, fam. You see it as a brick solid, yeah. That's because of this situation in it. So metallic bonding is occurring. There are many metal ions here, well, metal ions here, but atoms here with the nucleus, positive nucleus, and these delocalized electrons, they become delocalized, yeah, and it creates a sea around them, and that sea can basically move around, and hence that creates a very electrostatic force of attraction here between the positive nucleus here and the electrostatic here, and not what am I talking about, fam? It's getting late. Yeah, and the electrons around them, yeah. So that's why. The greater the charge on the positive ion, yeah, the stronger the attractive force as electrons are released into the sea. So deep it, yeah. If the ion has a higher charge, like a two plus ion, yeah, that means it released two electrons, yeah. Whereas whereas a plus ion only released one electron. So if it releases more electrons, yeah, and the charge is higher, there's gonna be a bigger discrepancy, yeah? It's gonna be from 2 plus to 2 minus. That's gonna create a much stronger attraction compared to 1 plus and 1 minus. You might say, well, it's the same charge, but that's because the C of delocalization, again, it's not a one-to-one interaction, yeah? The C of delocalized electrons is a whole sea of electrons, whereas the ion is just a straight ion. It's like how in the periodic table, when you go across the period, yeah, the atom decreases in size, yeah? It's a similar idea. Ions, a similar idea that when you add protons here, you're still adding electrons, but it has a bigger effect because, again, you're adding protons, and that proton has an effect on all the electrons in the outer shell collectively. Ions that are larger in size here, such as barium, produce a weaker attraction due to their greater atomic radius here. So ions that are larger in size produce like barium here, for example, is pretty large here. And that's going to be have a weaker attraction because the great atomic radius here has a big atomic radius here. It's a longer distance for the positive ion to act on the sea of delocalized electrons. So therefore it's going to be weaker, yeah? Calm. Ionic structure. So substances with an ionic crystal structure have a high melting point and boiling point. This is because the electrostatic forces holding the ionic lattice together are strong and require a lot of energy to overcome. So as we talked about the NaCl have a lot of strong ionic bonds between them, and that's why they have this huge ionic structure here. When molten or in solution, ionic substances can conduct electricity here. In this state, the ions separate and are no longer held in a lattice here. They are free to move and carry a flow of charge. So when they're molten or in the solution here, they can conduct electricity. That's because the ions here, not the electrons, the ions. Make sure you have this correct here. The ions separate. So the ions can now move around, and that flow of charge, that flow of ions here, that creates electricity here. Ionic substances are often brittle. When the layers are distorting, right, like charges repel, which breaks apart the lattice fragments here. So when the layers distort, like the Na plus and the Na plus, that repels each other, and that's gonna break the compound here. Alright, calm. Metallic structure. So metallic structures are good conductors. A sea of delocalized electron is able to move and carry a flow of charge here. Metals are malleable, as the layers of positive ions are able to slide over one another. So due to this sea of electrons here, it prevents fragmentation here. And so hence the layers of positive ions can basically move fluidly, yeah. The electrostatic force of attraction are very strong and hence have a high melting points and are nearly always solid at room temperature, yeah. So at room temperature it's nearly always solid, yeah. Calm. Simple molecular, yeah. These are covalently bonded molecules held together by weak van der Waals forces, yeah, or London dispersion forces, yeah. Van der Waals forces, will come into this in a minute, yeah. That's basically an umbrella term of London dispersion forces, yeah, as well as induced dipole and that kind of thing, yeah. But in A level at this point, you only need to just call it Van der Waals or just London dispersion force, yeah, and that's about it, fam. These Van der Waals forces are very weak and not much energy is required to overcome, meaning that simple molecular substances have a low melting point. So these are just simple covalent structures, yeah, like I2 or something, yeah, just the I and I, iodine 2, something like that, just some simple gas here. Water has a simple molecular structure but has a high boiling point. This is due to the hydrogen bonding. So that's different because it has hydrogen bonding, which we'll come into in a minute. They are very poor conductors, yeah, obviously because of the weak force, but obviously it's still a conductor because it's fluid in a way, but they're very poor conductors in it. Alright, cool. So macromolecular structure, yeah. Substances that have a macromolecular structure are covalently bonded into a giant lattice structure. Each atom has multiple covalent bonds, which are very strong, yeah, giving the substance at a high melting point. The strength of the covalent bonds also makes the substance rigid, yeah. So for example, yeah, diamond, yeah. Diamond is made up of carbon atoms, each bonded to four other carbon atoms. Hence, diamond is one of the hardest materials known, yeah. So as you see, fam, you got the carbon connected to the four other carbon here, and yeah, and that's why basically, yeah. So because of those four that's connected to, this creates a big lattice structure, yeah. So it's bare strong in it, and yeah, they call this, like, you know what I'm saying, they say like pressure make diamonds or whatever, innit? Or whatever, you know what I'm trying to say. Graphite, yeah, graphite is made up of carbons bonded to three others in a flat sheet, yeah. The electrons are not used here again. Just, fam, listen, yeah, what you expecting from this video, bro, yeah. Except the flaws in it. Yeah, better a dime with a flaw, yeah, than a pebble without, fam. Electrons not used in bonding are released as free electrons here, which move between layers here. Hence, it can conduct electricity here. So as a result, the electrons that are not bound here, they're basically free to move, and hence it can conduct electricity here. There's a graphite here, and it's made up of carbon bonds, but bonded to three others here, like this, in flat sheets here, over each other. Shape of molecules, yeah. So each electron pair will naturally repel. So if you put an electron and an electron, they're gonna repel as much as possible in it, right? So if you put them in the same plane, they're gonna repel 180 degrees in it. Whereas if you add another one now, it's gonna repel 120 whatever, yeah, and it's gonna keep going, yeah. Any lone pairs provide additional repulsive forces, which changes the bond angles because lone pairs, yeah, they repel more. So the lone pairs, they're going to repel the bonding pair even more by 2.5 degrees, yeah. But this is minor if you just learn the actual shapes, yeah. So now, how to know what I want? So find the number of electron pairs, yeah. Then find how many bonding pairs. Then find how many lone pairs, and then that will tell you the shape if you'd memorized it, yeah. So let's actually go deeper into it. So first shape here. Now I did this in order, so it's easier for you to like write it down, yeah? So make sure you write this down. Name, yeah, linear. Bonding pair, 2. So that's two bonding pairs, yeah? Lone pairs, 0. Bond angle, 180. Example, BeClCl. Calm. As you see here, there's a 180 gap, fam. And as you see, it has two bonding pairs, whereas it has 0 lone pairs, yeah? Calm. Name, trigonal planar. 3 bonding pairs, 0 lone pairs, yeah? Bond angle, 120. Again, B is bonded to three things. The angle between each one is 120. Yeah? Has no lone pairs. Calm. Tetrahedral, yeah? This has four bonding pairs, zero E, zero lone pairs, yeah? And 109.5 bond angle, yeah? And this is an example here. So as you see, yeah, with this one, it's not that important. So it is important. You need to basically just there's only a certain amount of shapes that have this other dimensional structures, yeah? So where the line is shaded or the line is dashed, yeah? Make sure you just remember it, right? It can be in different orders, but just make sure it has two singles and one shaded, one dashed. Yeah, there's not that many you need to remember, so just make sure you know that. Yeah, trigonal bipyramid. Yeah, so bonding pairs is 5, lone pairs is 0, bond angle is 90, 120. Yeah, both buses that go northward. And here's an example. Yeah, is yeah, so there's example, there's a 90-degree angle, yeah, and then there's a 120 angle, fam, between the B and the B there, yeah. So again, bonded to five things, yeah, and 0 lone pairs in it. Calm, name, octahedral, yeah. Bonding pairs is 6, yeah. Lone pairs is 0, and then bond pairs 90, yeah. So again, octahedral is bonded to 6 things. Again, for this one, learn the structure here, yeah. So dash dash, filled, straight, yeah. Same with that as well. And calm, and the bond angle here is obviously 90 degrees, yeah? Six bonding pairs, 0 lone pairs, yeah? Calm. So now you know the main ones, yeah? All the way up to 6. Now let's get into the ones with lone pair electrons, yeah? So write these separately so you can memorize it better, yeah? And the people say, yeah, this is the type of thing that you like learn before the test or you learn before, like night before, but just make sure you pattern it in it regardless, yeah? V shape, yeah? So bonding, yeah, has two bonding pairs, two lone pairs, and a bond angle of 104.5. I know this picture is shit, so it doesn't show it, but obviously there's two lone pairs on the oxygen there. I don't know why it doesn't show it. So that's what creates that V shape. Imagine those two lone pairs are going to repel the bonding pairs even more, yeah? The bond angle is 104.5, yeah? So I should show it here, but there's going to be two uh, lone pairs here on the electron, on the oxygen here. Okay, like this one, you see? So this one here is a triangular pyramid, yeah? This has three bonding pairs here. So you see one, two, three bonding pairs, and then one lone pair. So two electrons is one lone pair, yeah? The bond angle is 107, yeah? Calm. Square planar, yeah? This has four bonding pairs, two lone pairs. The bond angle is 90 degrees, yeah? And it has this kind of situation. So here's the two lone pairs, one lone pair on the XE. And that's got four bonding pairs, yeah? And that creates 90 degrees, yeah? Easy. A lot of man don't mention that square planar as well. Alright, cool. Polarity. Polarity refers to the distribution of electrical charge within a molecule. In a polar molecule, there is an uneven distribution of electrons, yeah, leading to regions of partial positive and partial negative charge. So this occurs when there's a difference in electronegativity, yeah. So we need to get onto this idea of electronegativity, yeah. So electronegativity, yeah, is the power of an atom, yeah, to attract electrons in a covalent bond, yeah. This is a very important definition, yeah. You need to know about this, yeah, like the back of your hand. Again, this gets asked all the time, yeah. And so atoms with higher electronegativity have a greater ability to attract electrons. So it's very simple, yeah. Some atoms, yeah, some nucleuses, yeah, some atoms, yeah, atoms, better term for it, yeah, have a greater ability, yeah, to track the electrons in the covalent bond. So let's say two things are covalently bonded, yeah. There's going to be electrons shared in that covalent bond. those electrons won't be in the middle like it is in the diagram. Those will be pushing towards one of the two atoms, yeah? Does that make sense? And that basically depends. So, for example, in the OH covalent bond, yeah, the electron shared is not, it's not between the O and the H. You see what I'm trying to say? It's not just in the middle. It's going to be more to one side. Does that make sense? And that's due to electronegativity. If something has a higher electronegativity, yeah, the electrons are more drawn towards it, yeah. And electronegativity values increase across the period and decrease down the group. So basically, diagonally from the bottom left to the top right of the periodic table, that's how electronegativity increases, yeah. Calm. Van der Waals. So now we're going into intermolecular forces, yeah. So Van der Waals, yeah. These are called also London dispersion forces, yeah. This is the weakest type of intermolecular force, yeah. The strength of Van der Waals depend on the MR. The larger the MR, the more Van der Waals forces, yeah. Van der Waals forces are caused by electrons. So because they're caused by electrons, yeah, that's why if you have more MR, you have more protons and whatnot, you have more electrons, yeah? And therefore, if you have more electrons, there's more Van der Waals, yeah? The way Van der Waals work here, or London dispersion forces specifically, yeah? Now, I'm pretty sure in A level you need to say London dispersion forces, yeah? Not Van der Waals, because Van der Waals is a broader term, yeah? But essentially, yeah? In an atom, yeah? If you deep it, yeah? Electrons are going to be moving around all the time. And at one split second in an atom, yeah? An electron, the electrons might all be on one side of the atom. So, like here. The electrons, they're going to be on this side when they're orbiting, yeah, on one side. In another atom, they might be on this side. So now, the positive is going to be closer to the area where there's a lot of electrons on this atom, yeah, and that's going to create kind of like a bond, like a force between them in a way, yeah. And that's Van der Waals. As you can see, it's very weak, yeah, because like you're relying on electrons in like a split second of time being in a certain area, and the nucleus of another atom being in a certain area. So obviously, it's very like rare, yeah. It's very weak. Yeah. And this can also work, by the way, these negative here, if you think about it, these negative might also push the electrons away in the other atom, and that is called inducing, yeah? So it induces the polarity in another atom, yeah? But this is very weak, yeah? But that's how they basically work, fam. So, yeah, that's Van der Waals. Induced dipole, yeah? An induced dipole occurs when a polar molecule induces a dipole in another molecule. So, let's look at this, for example. This one, it might be a polar molecule, yeah? And this one is not polar at all, yeah? So, induced dipole is a broad term. Van der Waals can also induce a dipole, but you might have something that has a permanent dipole that can induce a dipole as well and something else. So induced dipole is not necessarily like a, it's a force in itself, but it shouldn't be like compared amongst them, yeah, especially like now, yeah. It's more of like a technique. So this has a dipole, yeah, whether that be because of electron distribution, like we just saw with the Van der Waals, yeah, or it could be that it's a permanent dipole, which we'll see in a minute, yeah. Now, again, when this other thing comes next to it, has no dipole right now. See the negative? The negative is going to repel anything that's negative in this atom, yeah, to the other side. And that's going to leave the positive area here, and that's going to make a force between them after. You get what I'm saying? So if that was electrons here, there's bare electrons here, there's no electrons here, and because bare electrons here repels electrons in the other molecule here away, so therefore there's now bare electrons here, and there's the nucleus is here, so it attracts. Calm. That's called induced dipole, yeah? Again, this is very weak here. Permanent dipole. So this is the second strongest type, yeah? Permanent dipole. This is a type of intermolecular force here that acts between polar molecules. So when there is a high difference in electronegativities, yeah, the bond is polar, right? So if I have something that's electropositive and electronegative, there's a big difference in electronegativity, yeah. That means that all the electrons, yeah, in the covalent bond are going to be pushed more towards one atom, yeah. And because of that, yeah, you have this delta plus and delta negative. Does that make sense? For example, chlorine, yeah, is very electronegative. What that means is it pulls the electrons in the covalent bond towards itself. So the Cl here will pull all the bonds here towards itself. Does that make sense? If it pulls, all the electrons towards itself, yeah, so that makes it negative in a way, yeah. So now the Cl is negative. Does that make sense? And the H plus will become positive, yeah. Now, because there's such a big electronegativity difference here, Cl like easily grabs all the electrons in the covalent bond, yeah? And because of that, that makes it permanently polar. And another HCl that's also permanently polar. Do you understand? So that's a permanent dipole because there's that like huge difference in electronegativity, yeah? And as a result, that creates this permanent dipole, yeah? Or dipole interaction here. That's the second strongest intermolecular force between the Cl minus here of this one and the H plus of this one, yeah? So there's intermolecular forces, yeah. So that's basically how this works. Does that make sense? Yeah. So it's a lot stronger than the induced dipole because these ones are actually permanent, whereas the induced dipole is kind of due to chance Van der Waal electron chance and just stuff like that. Whereas this one, the electrons are actually drawn towards the Cl permanently. Does that make sense? Calm. Hydrogen bonding, yeah. And this is the strongest type of intermolecular force, yeah. Hydrogen bonding only forms is basically a type of permanent dipole, but it's a special type of permanent dipole, yeah. So it only forms between hydrogen and the three most electronegative atoms, yeah. Nitrogen, oxygen, and fluorine. Molecules held by hydrogen bonds have a much higher melting and boiling point, yeah. So, so this is basically essentially, yeah, just a strong permanent dipole, yeah, because hydrogen is very electropositive, yeah. So it's very like not electronegative, yeah. And nitrogen, oxygen, and fluorine are the most electronegative. So you can imagine like the difference in electronegativity, yeah. And because of that, you call it hydrogen bonds, yeah. And a certain man, bruv, in my class even thought that hydrogen bond in year 13, yeah, year 13, thought that hydrogen bond, yeah, is like between the O and the H in my class, yeah, back in the days, yeah. Bruv, come on, yeah. It's nothing to do with that, yeah. These are intermolecular forces, are not real bonds, yeah. So the O is delta negative, yeah, and the H here is delta positive, yeah. And as a result, there's this hydrogen bond intermolecular force between the negative and the positive, yeah. That's how this works, yeah. Very simple, yeah. So this is polar molecule. H would be electropositive, O would be electronegative. H here would be electropositive, electronegative, and bang, that's a hydrogen bond, yeah. And these are very strong if you think about it. If you've ever been sitting in like a science lab, innit? If your school got science labs, yeah, and they might have like a tap here and a tap or just a tap in general in it, yeah. And like anywhere in your life here, you might see a tap here, and then a tap like the water droplets are fighting against gravity and they're moving down slowly, yeah. That's the hydrogen bonds that are causing that like cohesive forces between them, yeah, that make them stick together. So imagine how strong it is, yeah. It's fighting against gravity even. Eventually, like gravity overcomes it in it, but still, you see what I'm saying? So these hydrogen bonds here, they're pretty strong in it. Pretty sure that's it. Yeah. So that's it. Yeah. Easy, fam. Don't or bonding. Yeah. Pattern. Yeah. Just memorize all the whatever it's called. Memorize all the shapes in it, and yeah, shapes of molecules. Yeah. The rest of it is pretty pattern. Yeah. Intermolecular force. That's about it, man. Do the sheets. It'll be easy. Yeah.